Hello, welcome to Puzzle of the Week series where we test tricky Java code. I am Łukasz and today we'll be inserting elements to the hash set. Let's check if anything can surprise us here. We initialize hash set and then populate it with 10 objects of the user class. After that we validate the hash set size. If we take a look to user class, it implements comparable interface, it has one text field name, and it overrides three methods: equals, hashcode, compared to. It's apparent that methods hashcode and compared to are not implemented by following best practices. One returns always the same value, and second throws an exception. We did it only for the purpose of this puzzle, so please never do such code in production. Okay, so now we can run our test. As we can see, test passes. Now let's make a little modification. Let's increase number of users to 11 and rerun the test. This time test failed. When we take a look to the test output, we'll see that an exception was thrown from user compared to method. That can be a little bit confusing. We used HashSet, and as we know, HashSet uses hashcode and equals method for organizing its data. And here, from some reason, compared to method was invoked. When we go deeper into the stack trace, we'll see that method was thrown by hashmap. That may be also surprising, but can be easily explained. HashSet stores its data in a hashmap. So when we add new element to the HashSet, it is placed as a key in this map with dummy value present. Okay, we explained appearance of hashmap here, but we still need to find out why hashmap invokes compared to method. To do this, let's dive into the internals of a hashmap. Hashmap stores its data as an array of nodes. A node is a structure which contains key and value and may pointing to another node. Each array position is so-called bucket. As you can see, bucket may be empty or contain node or chain of nodes. It is also worth to mention about load factor. It's a floating point value between 0 and 1, and when percentage value of non-empty buckets exceeds load factor, then resizing occurs and number of buckets is doubled. Okay, now that we know a theory behind hashmap, let's consider how data was organized in our scenario. We initialized a hash set, which incurred hashmap initialization with default parameters: an initial bucket size equal to 16 and a load factor equal to 0.75. Because the hashcode method of the user class always returns the same value, all elements went to the same bucket. This data organization is not efficient. To explain it, let's see how nodes are chained in a particular bucket. In a node, we can distinguish the following elements: key value pair, hash value, which is used to distribute nodes between buckets, next value, which is a nullable reference to another node. So we can describe the organization of nodes as being in a list. Even though they are not placed in a linked list, they create a similar structure. Due to this, the pessimistic read complexity of the hashmap is ON, and indeed, this is our situation. Now it's worth to mention about special hashmap optimization introduced with Java 8. This version introduced JEP 180, which aims to optimize hashmap reads in cases when buckets contain many elements. Optimization can be applied only when the key implements comparable interface and can optimize read complexity to O log n. In such cases, the bucket is reorganized into a tree structure. As we can see, nodes are extended with a new fields for tree navigation, references for child nodes left and right, and reference to parent node. Additionally, there are fields for tree balancing operations like read and prev. It is worth mentioning that optimization occurs in specific circumstances. To apply it, the bucket size must be greater or equal to 64, and the number of elements in a given bucket must be higher than 8. As you probably suspect, this optimization is responsible for our test result. Let's go back one more time to our test. If we read stack trace again, we can find a method responsible for bucket reorganization to tree structure. It's 35bin. Let's go to this method. As you can see, we can distinguish it into two parts. First is responsible for hash map resizing and occurs in case when we have less than 64 buckets. And second is responsible for bucket transformation to tree structure. So let's place breakpoints in both places. If we go deeper, we will find a place where compare to method is invoked. So also let's attach breakpoint here. Additionally, let's attach one breakpoint line in place where we inserting new user. Okay, so now we can rerun the test in debug mode. As you can see, we inserted 8 users and nothing happened yet. Now we're inserting 9th user. This time resizing occurs because currently we have only 16 buckets. Now we're inserting 10th user. This time also resizing occurs because we have 32 buckets and it is still less than 64. And finally we're inserting 11th user. And this time we went to the second part of the function. And this drives to invocation of compare to method and causes an exception. That's all for today. We explained the circumstances under which a hash set can invoke the compare to method of stored objects. The key lesson from this puzzle is to take care of proper hashcode implementation because it has significant impact to hash set performance. In most cases, implementation generated by your IDE is the best option and should be your first choice.